How can we answer this question?
Number all the row. So each time the number should be 3 or more.
Yeah, each time three or more. Dice. No, yeah, dice roll four times. Each time has to be three or more. So that means there are four possibilities, right? Three, four, five, six. Right. So when you roll one times, having three or more spots, probabilities 4/6. So you can
Yeah, multiply it
multiply it
4 times.
maybe four times. That's right. Then the probability that none of the rows show three or more spots. One
Two,
minus.
no, 2 over 3, 2 over 6 into
Yeah, no,
4
yeah,
times.
none of the, yeah, 2/6 to the power, not two, yeah, two.
None.
Yeah, yeah. And this one, not all the rows show three or more. Not all rows show three or more spots. This one says all the rows show three or more spots. This is not all, so that is the complement of the first one. So one minus the probability of the first one. Okay. A dice roll 10 times, find the chance of getting 10 sixes, not getting 10 sixes, all the rolls showing 5 spots or less. So how do you get the probability of getting 10 sixes?
So every time you need 6.
Yeah.
1 out of 6 into the power 10.
Power 10, right. So not getting 10 sixes is,
1 minus.
yeah. And all the rolls showing 5 spots or less. So you can do the same thing like this. I'm going to first find out what is the probability of getting 5 spots or less in a one roll. So that is 5/6, and that to the power 10. Which of the two options is better? Who are they the same? Explain. You toss a coin 100 times. On each toss, if the coin lands heads, you win $1. If it lands tails, you lose $1. The second one, you draw 100 times at a random with replacement from a box containing two tickets, 0 and 1, written on them. On each draw, you are paid the number of the ticket. Which option is better? In the first one, you either win or lose.
Yeah.
In the second one, you are only winning,
No,
not
nothing.
losing. So definitely, the second one is better. In the box shown below, each ticket should have two numbers. So 1, 2, 3, 4, 5, 6, 7. There are 8 tickets. Some numbers are missing here. A ticket will be drawn at random. Can you fill in the blank so that the two numbers are independent? So that means if you consider some event regarding the first number and another event regarding the second number. For those two to be independent, what should be the numbers here, here, and here? That is the question.
First one should be 1.
One. Here?
Yeah.
One. Okay.
And second one will be 1, 3.
This one.
Yeah. 8, no, 6.
to happen. So for example, if you say first number is denoted by n1, n1 can be here 1 and 3 in the first number, so there are only two possibilities. Second number is 2, n2 say for example. So that is related to this one 2, so we don't know, right? But for these two to be independent, probability n2 given n1 should be the same as probability n2, for example. Right? N1 given n2 and the same as probability n2, then we can say n1 and n2 are independent. For that to happen, we already have 1 and 2 here, two of those now. Right. So the other ones also we have to have 2 each, right? So therefore, we have 1, 1, 3. So therefore, this should be 3 also. Then you have 1, 3, and then you can have 3, 1 here and 3, 2. So 3, 1. So each should have the same number. So then in that case, when you calculate this probability, they will be the same. Or you can say that the probability n1 intersection n2 should be equal to probability of n1 times probability of n2. So that should happen. That will happen only if you have same number each. Okay. Let's look at this. You are thinking about playing a lottery. The rules: you buy a ticket, choose 3 different numbers from 1 to 100 and write them on a ticket. The lottery has both box. Lottery has a box with 100 balls numbered from 1 to 100. 3 balls are drawn at random without replacement. If the numbers on the 3 balls are the same as the numbers on your ticket, you will win. Right? Or it doesn't matter. If you decide to play, what is your chance of winning? That means your 3 numbers doesn't matter, but you should have the same 3 numbers as the numbers drawn, 3 numbers drawn on the books. So what is the probability of winning, like having a lottery with the same 3 numbers?
Uh, 100 into 99 into 98 divided by 100 to the power 3.
No, we don't do it with replacement or without replacement. Without replacement. You have different numbers, you just draw 3 numbers, no, it's like without replacement. So it's just like only one number will win, right? There are
Yeah.
how many possibilities altogether? Different numbers. How many different numbers?
100 to the power 3.
Yeah,
So 1 now.
one number. Yeah, one number. One C. Right. A pair of dice are thrown. Find the chance that both dice show 3 spots. Find the chance that both dice show the same number. Right now, this is just a very grade 5 level question, right? Using this picture like this, you can answer, right? The first dice and second dice, how many possibilities of the 36, right? So that's very simple question. So both have 3 means 1 out of 36. So like that you can find out. Or you can use the probability rules also. Right? In that case, the numbers are independent. We just multiply the probabilities. Right. In the game of Monopoly, a player rolls two dice, counts the total number of spots, and moves that many squares. Find the chance that the player moves 11 squares. So, my answer is written here. So there are only two possibilities, 5 and 6 and 6 and 5. So they are both two out of the digits. Right. True or false? If a, the last question. If a die is rolled 3 times, the chance of getting at least one ace is that correct? Probability of getting at least one ace. So it's what they have done is the probability of getting one ace means one, right? In so they have just added the numbers. Is that correct? If you die, if you roll a die 3 times, the chance of getting at least one is.
Please, it says
No.
at least one. So,
At least once is actually you can find out 1 or 2 or 3 separately and add them up. The easy way is to find out 1 minus none of them is ace.
right.
So the first one is not a ace, second one is not a ace, third one is not a ace. 1 minus that thing will be equal to this probability. So what is the probability that in the first one is not a ace?
5 over 6 to the
Yeah,
power.
so, yeah, 1 minus 5 over 6 to the power 3. Yes. If a coin is tossed twice, the chance of getting at least one head is 100%. Definitely wrong, correct? But how do you calculate the probability? Coin is tossed twice, the chance of getting at least one head is again similarly one can say 1 minus the probability of getting not getting any head. So 1 minus, the first one is a tail and second one is a tail. 1 over 2 to the power 2, 1 minus 1 over 2 to the power 2. Right. Okay, yeah. So those are coming from chapter 13. This is chapter 14. The chance of A is 1 over 3. There is another unit B, 1 over 3. True or false, the following. If A and B are independent, they must also be mutually exclusive. Is that correct? You can actually answer even without looking at the numbers, or if you want, you can do some mathematics. But even practically thinking also, you can answer if A and B are independent, they must be mutually exclusive. Should it be like that or not? No, no. There can be two events independent, but they can happen at the same time. So therefore, they don't have to be mutually exclusive. There are events which A and B are not dependent, but they can happen at the same time. So independent doesn't mean mutually exclusiveness. What about the second one? If A and B are mutually exclusive, they cannot be independent. Is that correct? If A and B are mutually exclusive, they cannot be independent. That means they cannot be independent means they should be dependent. So in other words, asking if A and B are mutually exclusive, should they be dependent?
I think yes.
Huh?
I think yes, because maths. So PA intersection B must be 0, so that if they are independent, they should be PA into PB. So then either way, PA or PB must be 0.
Yeah, yeah. But practically also you can just think like this. If A and B are mutually exclusive, what does it practically mean? That means if A occurs, B cannot occur. If they are mutually exclusive, that means if A occurs, at the same time they cannot occur. So if A occurs, B cannot occur. Or if B occurs, A cannot occur. So therefore, whether B occurs or not depends on whether it has. So that therefore, if A and B are mutually exclusive, that means they must be dependent. They cannot be independent. Or they can't not තනික වෙන්න බෑනේ. They cannot dependent. Being one තනික වෙනවද නැද්ද කියන එක හදාගන්න. So if A and B are mutually exclusive, they must be dependent. That means they cannot be independent. That's correct. Yeah, mathematically you can show see that. One ticket will be drawn and done from each of the boxes. Find the chance the number drawn from A is larger than the number drawn from B. What is the easiest way to answer this question? You can find out using the condition also, right? You want the probability A to be greater than B, so you can look at, you can condition on the value of B, and then the total probability of that is one possibility. But even you don't have to go like that, you can just draw a graph like this, look at the possibilities, 1, 2, 3, 1, 2, 3, 4, right?
Yeah.
And then figure out how many are in this particular set, right? That is the easiest or very low level one. But this, if you use the rule, this then you have to say, for example, probability A greater than B, given, for example, A greater than B, given that B is equal to 1 times probability B is equal to 1 plus probability A given B greater than B given B is equal to 2 times probability of B is equal to 2. Like that, you can look at the total probability below and then calculate. Right? So that you get the same answer. Probability A given B given B equal to 3. 3 වුණොත් බෑනේ 3 වුණොත් වැඩි වෙන්න බෑනේ. So මේ දෙක විතරයි එන්නේ. B1 or 2 විතරයි එන්නේ. Right? ඔය දෙකකින් ගත්තාම තව probability වෙනවා. So you can use this. Similarly the other ones. Right. So let's look at this one. Four rows are going to be made at random with replacement from the box. Find the chance that 2 is thrown at least once. 2 is thrown at least once. 4 rows with replacement. So when you say at least once, it's always easy to look at the complement. Not having at least not having at all. 2 is not having all the times number not equal to 2. Right. So 4 rows are going to be made with replacement. එතකොට පළවෙනි එකට වෙන්න පුළුවන් chances තියෙනවා
2 or 5. 2 or 5 from the first row. Getting
Yeah.
2.
Yeah.
Getting 2 from the second row. With replacement. So,
With replacement, so the
so
same,
yeah.
same times power, right? So 1 minus that probability, you are calculating getting a number not equal to.
No, I was talking about getting 2.
Getting to.
From the first row, chance of getting 2 is 2 over 5. And,
Yeah.
And from the second row, getting
No, අපිට බලන්න ඕනේ at least 2 නේ. එහෙම කිව්වොත් එහෙම 1 2 දෙකේ එකක් තියෙන ආකාරයක් හොයන්න වෙනවා දෙකේ.
no, the first one doesn't. So, දෙවෙනි draw එක සලකද්දී පළවෙනි draw එක අදාළ වෙන්නේ නැහැ. මොකද replacement දානවා.
Oh, what is the chance that two is drawn at least once? Two is drawn at least once කියපුවාම එකපාරක් දෙකකින් ඉන්න පුළුවන් දෙපාරක් දෙකකින් ඉන්න පුළුවන් තුන්වර ලේසි වැඩි තමයි ඒ ටික කොහොමද දුවන්නේ සම්බන්ධ ඒකට ලේසි එකපාරක් දෙක නොලැබීමේ සම්භාව්‍යතාවය වань වලින් අඩු වෙනවා. ඒ කියන්නේ හරි. එතකොට පළවෙනි එකට වෙන්න පුළුවන් chances තියෙන 3යි. numbers තියෙන 3යි. දෙවෙනි එකට වෙන්න පුළුවන් numbers තියෙන 3යි. තුන්වෙනි එකට 3යි, හතරවෙනි එකට 3යි. එහෙම ගන්න පුළුවන් මේ classical probability වශයෙන් යන්න පුළුවන්. එතකොට 3 times 3 times 3 divided by
4 5 times.
yeah, that's right. So like that, or you can take the probability and then multiply also 2 divided by 5 times 2 divided by 5 this because independence. The coin is tossed 10 times, 2 or 4s. The chance of getting 10 heads in a row is 1 over 1024. Given that the first 9 tosses were heads, the chance of getting 10 heads in a row is 1 over. Is the first one correct? The chance of getting 10 heads, yeah, 1 over 2 to the power 10. Yeah, that's correct. Second one. Given that the first 9 tosses were heads, the chance of getting 10 heads in a row is 1 over 2. Yes. So it doesn't depend actually what the previous one. So what we need is the last one to be head or that's just 1 over 2. In a lotto, 653 is just the name of the game. There's a box 53 balls numbered from 1 to 53. 6 balls are drawn at random without replacement from the box. You will win the grand prize if the numbers on your entry ticket are the same as the numbers on the 6 balls. Order does not matter. Right, so the first one has had 2 tickets with these numbers. Second one has have 2 tickets with these numbers. Which person has a better chance of winning, or are they the same chances? Just one combination will win.
Yeah.
Right. So
Same.
same chance, right? I mean, no matter what the numbers are, because these all are different numbers anyway. Right? So all have the same chance. First person has a certain chance because he has 2 tickets. The same chance for the second person because he also has 2 tickets. So what is that probability that any person? What is the probability of winning when they have these 2 tickets? What is the probability for this person to win?
1 out. So for 1 ticket, that's 1 out of 53 C6.
Yeah. That is for 1 ticket. So, but he has 2 tickets, so he may win from this one or from this one. So
Multiply.
yes. Right. That's it. So good. So can we go to the next chapter? We did this one. So today we look at one model called binomial model. So as I mentioned the other day, there are several ways of calculating probabilities: classical method, the relative frequency method, and then modeling like various models and so on. So here we're just going to look at one possible model applied in most of the times called the binomial rule. That's just a formula that you can use. Right? You can calculate the probability always using probability rules. So we have made up a formula using the rule, and we can then use the formula instead of calculating by looking at large number of possibilities. But before we come to the binomial, I will just introduce few words here, because this is when you talk uh, technically, these words are important. So Bernoulli trial is a word that we need. Bernoulli trial is any experiment. It's a random experiment where there are only two possible outcomes. That's that's what we call a Bernoulli experiment, like tossing a coin, head or tail. So that's a Bernoulli experiment. Recording whether a student pass or fail. So that's a Bernoulli experiment. So like that, deciding whether a product is defective or non-defective. That's a Bernoulli experiment. Like that. Generally, we call these two success and failure. Generally. So binomial distribution comes when if you consider a fixed number of Bernoulli trials. Suppose you carry out this particular experiment, where each outcome is always a success or a failure. You do it fixed number of times, say n times. You do this experiment n times, and then suppose you count the number of successes in n trials, number of successes in n trials. So if you denote the number of successes by, say, for example, x, n is the number of trials and x is the number of successes. What are the possible values for x? X can be 0, can be 1, up to n, right? So there are several possibilities of events, right? One event is x equal to 0, that is an event, that the number of successes is equal to 0. Another event is x equal to 1, right? So like that we can talk about n plus 1 events, n plus 1 events. So generally one might be interested in some of these, the probability of some of these, or maybe all. Right? So what we call the binomial distribution is just single formula that gives the probability of any of these generally. So if you want to find out probability is equal to 0, we should be able to get that probability using that formula. Probability x equal to 1 from the same formula, probability x equal to n from the same formula. So that's what we call the binomial formula. So let us just look at, let us derive it by ourselves using the probability rules. Suppose we are generally interested in finding the probability that capital X is equal to, say, some value simple x. Yeah, simple x can be 0, 1, 2, up to n. Right? So let's just take one value x. Suppose now in this case, if you want to apply this particular distribution, there are some conditions under which we can apply this model. Right? So the first condition is we should have a fixed number of Bernoulli trials, fixed number. And then the outcome in the Bernoulli trial outcome is always success and failure. The outcome should be independent also. Whether what you get in the second one doesn't depend on what you got on the first one. What you get in the third one should not depend on what you got on the first one and second one. That is another requirement, independence. The third one is the probability of getting a success in any trial should be the same always. Probability of success should not change from trial to trial. Right. So if these conditions are satisfied, then we can derive a formula to calculate the probability. So assuming those three, let us derive a formula for this probability x being equal to simple x. So that means we have to look at the ways of happening simple x number of successes in n trials. Right. So that means x number of those should be successes, n minus x should be failures. Right. So how many ways can that happen? First of all, How many ways can that happen? For example, this success can be in any place. No? There are in boxes like, right? We should be looking at how many ways we can put X number of successes in these n boxes, right? So then the other way, other boxes we have failures, right? So how that means selecting, right? Number of ways of selecting some places to put X's out of X. You have to select X places out of N places to put successes in NCX. So there are NCX of ways of happening this event, X being equal to simple X. Right? So let's consider one of those, for example. So a success may be here, success may be here, and then success like that. So all the others are failures. So X of those are successes, the others are failures. So what is the probability of happening that? X number of successes and n minus X number of failures. All these are independent. So therefore the probability of happening all those together is equal to the probability of a success. Let us denote the probability of a success by say Greek letter theta or maybe p, but because I use p for the probability, I will use something like this. So if the probability of a success is in any trial is theta, then the probability of failure is 1 minus theta. So therefore the probability of happening this should be
theta to the power x
theta to the
into
power x,
theta.
1 minus theta to the power n minus x. That is only one way. So there are NCX ways of happening that. So you have to add right this way or the other way or the other way. So those are mutually exclusive. So therefore we can add the probabilities. So therefore the final answer will be NCX theta to the power x 1 minus theta to the power n minus x. Right. Where this x can be 0, 1, 2 up to n. So that is what we call the binomial formula. Binomial formula. So this can be used to calculate the probability of a given number of successes, X number of successes in n Bernoulli trials. Right? We have to know the value of n, of course, we have to know the value of theta, and we have to know the value of x, simple x we are looking at. Here the capital X denotes that is called the random variable. Right? It's a variable, it is the number of successes in n trials. So in this case we say x, capital X, that is the number of successes, the variable has a binomial distribution. Right? It has a binomial distribution. So that is the name of this particular probability distribution. Right? So this formula tells you how the probabilities are distributed at these values. Right? If you add all these probabilities, probability x equal to 0 plus probability x equal to 1, probability x equal to 3 up to probability x equal to n, that will be equal to 1. Right? So this formula tells you how the probabilities are distributed. The probability of 1 is distributed at these values. So this is also called the probability mass function. Probability mass function of a binomial distribution. It gives you the probability mass at each possible value. So we can use this formula in lots of situations. If we can model our problem as we have to have some experiment where we can consider n Bernoulli trials, and then our variable of interest should be, we should be able to model it as the number of successes. So it is not virtually success, it can be failure practically, but in order to answer the question we formulate it as a success. So therefore x is the number of successes And in that case, we say that there is a distribution for x. X has a binomial distribution. This is the usual notation because in order to calculate this probability using the formula, we must know the value of n and value of theta. Of course, simple x will be specified in the problem. We are interested in how many successes, but in order to calculate, you need n and theta. So therefore, usually we denote it like this. So one might say x is binomial with 10 and 0.2 in a problem. So that means that's we are considering 10 Bernoulli trials, where in each Bernoulli trial the probability of our success, whatever we define as success, is 0.2. And then we can calculate what the probability that x equals 0, what the probability x equal to 1, like that up to the probability x equal to 10. Just by using the formula, right? Otherwise, we'll have to think, okay, how many ways that can happen and so on. So that we can do that way also, but this is easier. Right? That's actually kind of a modeling. The thing is actually there are situations where these conditions, binomial conditions, may not be satisfied exactly, but still we can use the formula to calculate the probability approximately. So let me explain that a little bit. For example, suppose you have a box of things. Suppose you have some white balls and black balls. Certain number of, we are given the number of white balls and black balls. And suppose we are taking a sample of 5 balls out of this. Right? Maybe there are, say, 3 balls and 10 balls like that. Suppose we are taking 5 balls without replacement. In that case, so the outcome in each trial, so we can we consider taking a ball as a Bernoulli trial?
Theta is different each time.
No, we can actually, Bernoulli trial is defined as an event which has only 2 outcomes. Right? So for example, if you take one ball, it's going to be either white or black. So therefore, you can consider it as a Bernoulli trial, but the outcomes are not independent. Those trials are not independent. That's a different thing, right? Bernoulli trial. But some people, I have seen that independence is also considered as a part of the Bernoulli trial. But usually, Bernoulli trial is an experiment which has 2 outcomes. So if you take a ball, for example, you can define one event to be having a white ball, the other one is a black ball. So if you define like that, the experiment is a Bernoulli trial. Right? But if you take with replacement, now suppose I want to look at number of white balls in my sample of 10 balls. In that case, I cannot say a number of balls in my sample if you define it by x has a Bernoulli distribution, sorry, binomial distribution. Because in that case, outcomes are not independent. But if you consider the experiment where you are taking the balls with replacement, right? If you take with replacement, then if you define x to be the number of white balls, for example, in your sample, in that case you can use this formula to calculate the probability of getting a given number of white balls. What the probability is, there will be 0 white balls in your sample of 10, right? Those conditions are satisfied. Because the probability, there are only 2 possible outcomes, in that case white and black. Whether you get a white or not in the first one doesn't depend on second one, doesn't depend on what you get out on the first one, and so on. Because with replacement, the probability of getting a white ball, if you define getting a white ball as a success, probability of success is the same in each trial. So in that case, you can use this model. So like that is one situation. If you're taking from a finite population, where you can categorize the elements as success and failure in general. If you take with replacement, right, and then if you are interested in the number of successes in the sample, you can use the binomial model. If you consider taking a sample without replacement, in that case binomial model is not suitable. You have to, there is another model called hypergeometric distribution. Hypergeometry. it's not in the syllabus, but I will mention that if you want, we can get a formula for that also. Right? In that case, binomial model is not suitable, right? Without replacement. Or if you have a very large population, right? If you have a very large population, say for example you have 10,000 items in a population, you take 10 items out of that, right? Now in this case, whether you are taking with replacement or without replacement is not that a big problem, because the probability of getting a success of, for example, suppose you have 10,000 items in a lot or batch of items, you are going to look at whether the items are defective or non-defective. So your experiment is to decide whether the item is a defective or non-defective, but you are taking only a sample of 10 items. Right? So now in this case also, actually whether first one is second one is a defective or not depends on whether the first one was a defective or not. If you take sample of size 10, because for example, suppose you have 9,995 good ones and only 5 bad ones in the population. So the first one is a defective one with 5 out of 10,000. If the first one is a defective one, the second one is defective is not the same, slightly different. But still, in that case, we just consider them as the same, because the change and the probability, even though they are not really the same, they are very close. So therefore, in that case also, we can use the binomial model if you want to calculate the probability of success, the probability of getting how many defectives, number of defectives in that particular sample. Right. So therefore, of course, if you are taking with replacement, ideally the model will be okay. Even if you are taking without replacement, if the population is very large, still we use the binomial model to calculate the probability of success in the sample. So let us look at one or two examples just to understand this further. Suppose that 4 products of 10 products in a box are defective. So 4 are defective, therefore 6 are non-defective. Consider the experiment of taking a random sample of 3 products, one by one, with replacement. So because you are taking with replacement, this actually satisfies the binomial conditions. Let Di be the event that ith randomly selected product is defective. So the D1 is the event that the first item is defective, D2 is the event that the second item is defective, D3 is the event that the third item is defective. Okay, whether I'm asking actually this question that I gave to my students in university. First of all, A naught is the event that the sample contains 0 defective products. I mean, whatever only I just wanted to derive the formula and then now for us actually we can directly talk about A naught. A naught is the event that the sample contains 0 defective product. What is the probability of A naught? In other words, I can ask what is the probability that the sample of 3 items contains 0 defective products. E1 is the regarding the sample contains 1 defective product. Therefore, both questions can be answered if I define the same random variable. The random variable of interest is the number of defective products in the sample. So this one is asking what is the probability. So if you say X is the number of defective products, in the sample. First is asking what is the probability that X is equal to 0. Second is asking what is the probability that X is equal to 1. So you can use the binomial formula. What is the distribution of x in this case? X has a binomial distribution with n is equal to, we are taking a sample of 3. So therefore n is equal to 3 here. You are taking with replacement, therefore what is the probability of getting a defective item in any trial? 4 out of 10. So it's point. So therefore I know the value of n, I know the value of theta. So I can just calculate, this is a simple x here, simple x. So this is 10c 0, 0.4 to the power 0, 0.6 to the power 10. If you apply the formula here, 10c 1, 0.4 to the power 1, 0.6 to the power 9. So like that you can get any probability. So that's a good thing, using the same formula. Okay. So derivation we have already done. Okay, let's try to answer a little bit different than the previous one. Let's answer this question. I'll give you a few minutes. Right. For you to try. It's not difficult actually, it's easy. According to the past data, 5% of all TVs of a certain brand are submitted for service while under warranty. Of these, 75% can be repaired, whereas the other 25% must be replaced with the new units. A shop has sold 4 of these TVs. What is the probability that at least one of those TVs will be returned for service during the warranty period? Return for service. So you are interested in the number of TVs that are returned out of 4. The sample size is 4. The probability that any item will be returned is 0.05. So in this case, theta is equal to 0.05. Your question is, what is the probability that at least one of those TVs is returned? So if you say x, let x is the number of TVs returned for service, then we can say x has a binomial distribution with n equal to 4 with probability of a success. In this case, success is not real success, but according to our model, we can say, because that's the event of interest, x has a binomial distribution with this. So the question is, what is the probability that x is at least 1, right? So greater than or equal to 1. So you can answer this in the long method or short method also. The long method is you can calculate the probability x equal to 1 plus probability x equal to 2 plus probability x equal to 3 plus probability x equal to 4. Each one can be obtained using the formula. What is the easy method?
1 minus.
1 minus, yeah. 1 minus probability x equal to 0. You have to get only one value. Right. Okay, part 2, how would you answer that question? What is the probability? At most, one of those TVs sold last week will have to be replaced with a new unit free of charge. So, out of those TVs returned for service, 25% are going to be replaced. So, therefore, for all the TVs, for any TV, what is the probability that any TV will be replaced? any TV will have to be replaced is equal to 0.05 times 0.25. So now we are interested in a different random variable. We can say, for example, y. Y is the number of TVs that will be replaced. So the success is being replaced, failure is not replaced. Still, we are looking at these four TVs that was solved in the last week. So therefore, we can say y has a binomial distribution with n equal to 4 and theta in this case equal to 0.05 times 0.2. That is the probability of success. So the question is again, at most, one is the probability y less than or equal to 1, at most. So that is equal to probability y is equal to 0 plus y is equal to 1. So both can be obtained from the formula. So that's convenient because you can directly use the formula once you model your problem, once you decide how many boundary trials and check whether the conditions are satisfied. Now in this case, why can we say that they are independent? Because we just think of a large population, right? All the TVs produced, right? So this here we are not talking about a small set. Right? Sample is taken from a large population, therefore uh, we assume that the probability that any TV will have a success is the same and they are independent. Okay, let's try this one. A bulb manufacturer sells small Christmas bulbs in boxes of 6 bulbs. It is known that approximately 10% of these bulbs are defective. Suppose that you buy 2 boxes of bulbs. What is the probability that the total number of defective bulbs in the 2 boxes is less than 2? Okay, yeah, okay, let's see. How do you model the problem now? What is your sample size? What is your theta?
N should be 12, theta should be 0.1.
That's right. Yeah.
So we
You are
should
looking at number of defective bytes less than 2. So that means
0.
0 and 2. Second one, you cannot do it manually. You need a bit of programming balls on computer. But suppose you need 50 non-effective bulbs for your task. In order for me to be 95% sure that your requirement is fulfilled, what is the minimum number of boxes of bulbs that you have to buy? So for this, you have to assume that the number of boxes of bulbs that you have to buy is like some number n, right? So then you may be looking at 6 times n bulbs, right? If your sample size is 6 times n, what you want is the number of non-defective bulbs to be greater than or equal to 50, because you need at least 50 now for your task. So therefore, if you have at least 50 non-defective bulbs, you are okay with it. So therefore, you want the probability of having at least 50 non-defective bulbs in 6 times n bulbs to be at least 95%, 0.95 probability. Right. So you have to look at you have to find out the probability of getting at least 50 good one bulbs by taking different n values. What is the I mean when you have n equal to 1, that can happen. So at least you have to have how many? You have to consider at least 50 or whatever in box 9ක් විතර ගන්න බැරුණු ගන්න 9න් එහා පැත්තට බලන්න 9ක් ආවොත් මේක වෙන්න පුළුවන් chance එක 50ක් හෝ ඊට වඩා වැඩි වීමේ සම්භාවිතාවය box 10ක් සැලකුවොත් ඒ සමානයි 10 නම් එතකොට කොච්චර කියලා බලපුවම පේන්නේ ටිකක් මුලදී වෙන්නේ නැහැ ටිකක් වැඩි වෙනකොට අපිට පේන්නේ යම් කිසි අවස්ථාවකදී ඒ probability එක 0.9 ඉතින් එහා පැත්තට 0.9 කට වඩා වැඩි වෙනවා. So the number of boxes, the least number of boxes that you have to consider will be whatever that is. So you have to calculate and maybe look at the probability of say x. If you say x is the number of non-defective bulbs, you have to calculate the probability that x is greater than or equal to 50 for different n's. Right? If n is equal to 9, 9, 10, 11, you have calculated, and then after some time, so earlier maybe like this, and then maybe when it is 12, it goes like that. So therefore, you have to have at least 12 boxes in that case if this is 0.95. So you have to calculate this probability again using the binomial formula. Then find out what the minimum number of boxes you should have for you to be 95% sure, at least 95% sure that you will have required number of bulbs for your task. Clear? Right. Okay. So that's actually the end of this section. Also, binomial formula, you just have to know the formula. And then you have to look at it's just an address. You just have to look at whether you can model the situation and whether you have binomial conditions and whether you are looking at number of successes. Right. We'll take a small break.